Hello children, this is a Unit 3 review video. I'm not going to be able to do all your reviewing and studying for you. You will need to go back and look through the notes, study the homework, make vocab flashcards for you, etc. But hopefully this can aid the reviewing that you're doing. But I want to emphasize it is not a replacement. Okay, we have 4 standards, these 3 plus the literacy. Okay, so standard A is just kind of knowing ionic covalent metallic bonding. Standard B is going deeper into covalent. Can you draw Lewis dot structures? And do you know polar versus nonpolar? And then standard C should be fairly straightforward. We didn't spend a lot of time on it, but it is its own standard, is can you connect the forces between solids, liquids, and gases? Okay, so we'll start with the biggest one, which is probably A. Alright, so let's talk about ionic. So in ionic you have 2 atoms, one with a high electronegativity and one with a low. This high electronegativity is really good at pulling electrons, so that's what it does. It takes an electron from the low and gains it. So what happens is the loser lost a negative, so now is positive, which is a cation. And then the high electronegativity forms a negative charge, which is an anion. And so now these attract each other, that's what this is, through the electrostatic force, through an electrostatic force. It's electromagnetic force, but electrostatic since they're not moving around. Okay? Electrostatic. But there's a whole bunch of these. And so what happens is these form a crystal structure where you have a repeating pattern of positive and negative, and you could just go on forever, or until you run out of atoms anyway. Okay, and so this is a set pattern, really, really strong forces. This is really strong. Really, really strong forces. And so these don't move because they're locked in place. Don't move. They're hard to melt because it's a really strong force. And since they don't move, they don't conduct. Conduct electricity, if that wasn't just implied. However, what happens if you dissolve it? Well, if you take there's some water. If you take these crystal and you dissolve it, what happens is the ions dissociate. I don't know if you want to take notes on something, it might help you pay attention. And so now we've got these positive and negative charges just kind of floating around, and now they can move freely, and so they will conduct. Okay, but otherwise, if they're not dissolved or if they're not melted, this would also work if it's melted, you're not going to see ionic compounds conduct electricity. Special note, remember the polyatomics. You need to memorize these. I gave you 6 of them. I can't remember which ones I gave you. I think it was hydroxide, nitrate. I probably gave you sulfate, carbonate, phosphate, and ammonia. Those are the big ones. I might have given you something else instead of sulfate, but I'd be surprised with myself. So usually it's always metals that are the ones losing the electrons, but in some rare cases, not actually that rare, you can have ammonium form the ion. So it doesn't have to be metal nonmetal for ionic, but it does have to be a cation and an anion for ionic. Okay, let's talk about covalent. So in a covalent, what happens is you've got 2 or more atoms with a high electronegativity. And so what happens is these both have electrons, and so this one, let's color code it, it tries to grab this, right? And then this other one, let's do blue, it tries to grab this. But the problem is no one wins. No winner. They share. Okay, and so you end up with these electrons, oops, I was trying to do green, with these electrons in between them, and they're both attracting these electrons. So this is a pole, this is a pole, okay, and so the forces in, I don't know, let's call it tug of war, in tug of war lock atoms together. So you can imagine if it's like you and your sister, you know, fight over the remote control. If you're both grabbing it really hard, then if you walk away, she's going to have to go with you because you're connected by those electrons, or the remote control, as it were. Okay, so these form molecules, which are small sets of atoms, because they don't repeat like crystals do. They don't conduct because the electrons are localized in the bond and can't move. They typically have low melting points since molecules don't attract each other well, although we'll go through some interesting exceptions. And let's actually come back to this because it leads into standard B, which is Lewis dot structures. So let's do metallic really quick. Okay, so with metallic bonding, you've got metal atoms with these electrons, and they're just like, they do this. They go YOLO, right? And then these electrons, they just fly off. Whoa, because both of these have low electronegativities. And so what you get is you get a whole bunch of cations, because now the metals have lost their electrons, so they're positive. So you just get a whole bunch of these, right? And they're all they don't have to be lined up. They kind of are, but it doesn't matter. Okay, I'm gonna do like one more row and then delete the rest because I just got too crazy with the copy and paste. But remember, there's electrons that they lost. I'm doing the electrons in blue. And so those are also moving around. And so these just kind of randomly go through, and they're not really locked in place. They're what's called delocalized. Delocalized electrons. Okay. And so this is kind of hard to draw, but what happens is you just get kind of this field of negative charge. All right. Oh, I should have. So I'm taking these blue things, just saying, you know, they're kind of everywhere. They're wandering around. All right, and so what you get is now this blue is just a field of negative, because these electrons are just constantly moving around. Like here, I'll wreck my drawing, right? These are just, it's constantly moving. There's nothing keeping them in one place because they have this low electronegativity. And so now these positives are attracted to this negative field and they kind of get stuck, okay? So I think the biggest thing to be able to explain with this is why metals conduct. Why? Because electrons can move freely. Alright, and electrons have a charge, you have a moving charge, thus conductivity, just like when we had the ions that could move around right there. I think the other thing is why malleable, because the electrons can move freely. And so the negative that the cations attract to can be everywhere. Right? And so if I take this one and I move it, oh look, it's still in the field of negative. What about this one? If I move it oh look, it's still in the field of negative. What if I hammer this so I squish it together to form a little sheet? Because I don't want my metal to be as thick. Well, oh look, it's still in the field of negative charge, so still attracted. Okay, let's go back to the Lewis dot structures now. So Lewis dot structures, 2 rules you gotta live by, okay? Don't magically add or remove electrons, and then you always need an octet, which I guess I should have led with in the beginning, because that's the whole reason that we're bonding, is because of this octet rule. Let's write that down somewhere. You always need an octet, which is the octet rule, which is full valence electron shells. That's what you're always going for. So let's say you have something like, I'm trying to think of a kind of challenging one. Okay, CO2, that's a challenging one. So you take the one that makes the most bonds, which is C, put its valence electrons in there, and then surround it with O, 6 valence electrons. There are 2 O's. Alright, and then you're going to want to start bonding these up so that they each have 8. So they both have high electronegativity, so they share like this. Carbon can't share with itself. I could bond these together, but then carbon's lonely, so I'll do this. And so I get carbon, double bond to O, lone pairs, O, lone pairs. Okay, and then last thing, I guess, is don't forget about the diatomics. Remember, have no fear of ice cold beverages, right? These all exist as pairs in nature, so oxygen is O2, that's what we breathe in. And we say oxygen, but we don't just mean O, we mean O2. Okay, polar, non-polar. So, whoa, yikes. Alright, so if we have an electronegativity difference, like HF, this one is more electronegative. What's going to happen is the electrons will not be dead in the middle. They'll be more slightly on the F side. So this becomes slightly charged, this becomes slightly positive. And so this is called polar. However, if you had something like CF4, I'm going to skip the lone pairs because I'm going to end this in a minute. I can't go over 15. The electrons, yes, are slightly more towards F, but what's happening is you have pulling this way and pulling this way, so they kind of cancel out, and so there is no positive or negative side here. So this is nonpolar, right? So essentially you check 2 things to figure out if it's polar. Are there dipoles? That's unequal electronegativity, and do they cancel? So are there dipoles is unequal electronegativity. Alright, and now let's talk about the phases. So there's 3 phases, right? Solid, liquid, or gas. And in terms of strength, solid is the strongest. Oh gosh, what happened there? Sorry. Is the strongest. Gas is the weakest, and you should know how to diagram them, so solid is all packed together. Liquid can move around but does not fill its container. It just kind of sits at the bottom. It takes whatever shape of the bottom it's at. And then a gas actually fills its container because it's so weakly attracted to itself that it just flies everywhere. They tend to be moving faster, all right? So if you have a solid and you add energy to it, you can eventually free it. Alright, so good luck on the exam. You don't need luck. Study hard.